Attention class, you're now looking at video 2 of 3. Now, what we're doing in this video is we're going to continue on with the chapter problem that we finished talking about. We talked about it, but we didn't crunch any numbers. And that's what we're going to do right now. Now, for those who might not be aware of what's going on for the chapter problem, what I'm going to do is give you guys kind of a brief reminder. This is the table that summarizes all of it. But long story short, the author was talking about how he purchased a new car, and yet the dealer said, you know, we're only going to install the rear mirror. I'm sorry, the rear license plate. Even though it's required, police officers don't bother to check. This baffled him, so he wanted to sit back and figure out whether or not states actually have differences in whether they enforce whether you have the front and rear license plate on your car. Now, in order to sit back and address this scientifically, he went out and collected data, which is depicted right here on this slide. Now, in order to solve this problem, we're going to use this equation. This equation is rather unique in the sense that we'll talk about this a little bit later, but it does originate, and it's very similar to what we've done in the past. I will show you how similar it is a little bit later. However, the equation that we're going to use is as follows. In order to calculate Z, to determine whether there is an effect or there's a difference between these two proportions, what we're essentially going to do in the numerator is subtract and calculate the difference between these two proportions. And then we're going to use the pooled sample proportion in the bottom to serve as an indicator of kind of like the standard deviation like we've always done with many of the Z-scores. Now, one of the things that's key, and many students don't do this, I'm actually hoping right now with me doing this in this video, you guys will know, but this part of the equation is referring to P sub 1 and P sub 2. Again, that's scientific notation. That's the population proportion. Now, in many times in the world, we don't really know what the population proportion is. We make estimates from samples. So we don't really know what the population proportion is. So one of the things that we do in this problem is we assume that P sub 1, P sub 2 equals a value of 0. So even though this equation looks really, really fancy when it comes down to everything in the numerator up top, we're really only focusing on this portion right here. And that's because we always assume with the problems in this class that this value equals 0. So we can write it out, but again, it kind of makes this equation a little bit easier to digest when you sit back and think about realizing that you can just ignore that portion of it. Again, which we talked about, I am not going to go into the confidence interval method. I think it's good enough for us to do with the hypothesis testing. So we're just going to stick to that approach while we do this. Now let me get rid of this annotation. Now, this is the data. We want to find out and calculate the pooled sample proportion. Now, as we talked before, we have to sit back and remember a very important aspect about when we're talking about probabilities, things are in one or two categories, and we refer to them as successes and failures. It's key. Cars with rear license plate only is successes. We need to make sure we know and remember that. Now, what would be our X of 1? Our X of 1 would more than likely be Connecticut, and our X of 2, or our second sample, would be New York. So our first sample and our second sample are these information is indicated right here. Now, in order to go in and calculate the pooled sample proportion, we're going to use this information that we have on the screen right now. So what I'm going to do is sit back and solve this. We got X sub 1. X of 1 will be 231. 239, I apologize. X of 2 is going to be a value of 9. I apologize. I know my handwriting is pretty bad. N sub 1, right? That's the sample size, right? You got to use a little critical thinking. Many people might run right to this number right now because it's the only other number they look at, but no, you have to think critically. We're looking for N is the sample size. The sample size for Connecticut is 2,049. The sample size for New York is 550. I always suggest that we take baby steps. When we take these baby steps, we're going to find out and see that this numerator right here is 248. And the denominator is 2,599. Now we do the math for that. We're going to get a P bar equal to 0.0954. Now we've talked about this a little bit before. This is one of the notation we want to use. I'm going to list this number to 3 significant digits. The 0 is not significant, doesn't tell us anything, right? The 9, the 5, and the 4 are, so that is where I'm going to stop. All right, now, we also want to calculate Q bar. That's going to be 1 minus our 0.0954, which gives us a value of 0.9046. Now, we want to sit back and attend to this pretty much for 3 significant digits. So essentially, we would kind of stop right here. And since we're going to stop right there, then we want to make sure that we should round this value up to a value of 0.905 equals our Q bar. So that's our value of Q bar and also P bar when we're plugging in those numbers. Now, I'll tell you, I wish it stopped there, calculating the pooled sample proportion. However, it gets a little bit more tricky. We now need to calculate, when we're doing a hypothesis test, we need to calculate Z. Now, if you remember from what we talked about before, we can assume that this portion of the equation equals 0, right? So we just plug a little 0 there because of what we talked about right here. Now, we need to figure out what the values of P hat are. Now, P hat is the proportion of values that are successes in the first sample. P hat 2 is a proportion of values that are successes in the second sample. Going back to our data and our information, we can sit back and see that would be 239 divided by 2,049. For New York, it would be 9 divided by 5. Now, when you do the math for those things, you're going to have these values right here. You can double check. This is the math of 239 divided by 2,049. And this right here is the math for 9 divided by 550. That is the math. You can double check if you want. I actually encourage you to. Now, what I ended up doing with this is we needed that for this equation. So calculating P hat and for sample 1 and sample 2, right, since we know this equals 0, right, is needed. So we can rewrite this equation, the numerator, as 0.11 minus 0.016. Now, we already calculated our P bar and Q bar, which is right here from the last page, 0.095 and the 0.904. Now, we can round these values up a little bit. And also, if you look at this equation, we need to multiply these values. As you can see right here, our task is to multiply in this numerator right here, P bar times Q bar. So we have the values here and here. And what I'm doing right here is I'm multiplying them. So this right here is multiplying those two values, and it gives us this value. The reason why I'm doing this on the side is because if you look at this equation, you'll see that P bar is used twice. P bar times Q bar is used twice. So calculating them off to the side and just referring back to this number of 0.0859 will save us a little bit of time. So when I'm going into my equation, I'm not even going to save us a step. We know that the 0.0859 is going to be atop of both of these values. Then we again have the 0.0859. N sub 1. N sub 1, going back to that first problem, is our 2049. That looks bad. And then N sub 2 is our 550. Now, I always encourage when you do these problems to take baby steps, right? So the first baby step that I sit back and see and think is important is to sit back and calculate this numerator over here. The numerator, when we do that, it's going to give us a value of 0.0997. Next baby steps that I would argue would be to do these problems right in here. Calculate this, and then also calculate that value right here. When I do those calculations, I get a value of 0.0000. Believe it or not, this is where the significant digits come in, 419 plus 0.000. Yes, this is where our digits come in, 156. Again, we stopped as soon as we got 3 significant digits. And as I've said before, the zeros are not providing us with any information, so we don't consider them as significant digits. Now, we cannot forget, and I think I see people do this a whole lot, we cannot forget the square root over there. Now, the next baby step that I would argue, and I think many of you guys would agree, would be to calculate this value right here. When I do that, I get a value of square root of 0.000198. And again, that's over. Let's not forget our 0.0997. Next baby step would be square root of this. 0.0997 over the square root of that is 0.0140. The last baby step is all that's left. We get a value of 7.12 equals our Z. The difference between these gives us a Z-score of 7.12. That's pretty extreme. pretty extreme. It's a lot of math for this problem, but this is all that's needed to sit back and calculate and to use that equation. Now, the one thing I'll say before I go right here is this. I want you guys to sit back and remember how our distributions are. Remember, we have distributions that look like this. In the middle of the distribution is a value of 0. Then we have a value of 1, 2, 3. And I think you guys know, kind of up here in the tail end, around 1.64 is kind of where we get our alpha equals 0.05. And we would say that our value is significant. Right around here at like 1.64. I just want to let people know and understand what we just calculated. What we just calculated with this z-score, we just found out that the z-score difference that we have is not 1, 2, 3, 4, 5, 6, 7.12 is where our z-score is. As you guys can imagine, 7.12, this is absolutely significant as a result of being so extreme and this far off to the side. Now, the last thing I want to do is kind of give you guys kind of a reminder about what it is that we're doing and why this formula can be used. As we mentioned before, we can disregard the aspect of this right here because we're going to assume that this right here is 0. Because we never really know the values of the population. But one of the things that we've talked about before in 6.1, and again, these things build on top of each other, and we also talked about it on 7.1, is the fact, right, that when we're using a distribution of proportions, even though it is technically a binomial distribution, right, as opposed to being continuous, we can approximate a distribution of proportions with a normal distribution. But when we do it, it's a little bit different. The mean isn't going to be X bar. The mean is going to be the proportion value of P. And the standard deviation is not going to be our standard deviation, but it's going to be the square root of P times Q divided by N. This is what we've done before. Now, I want to sit back and bring your attention to this just a little bit. Why? Because this P right here, now granted, we're comparing two different samples when we're doing this technique in 9.1, but as you can see, the numerator of this z-score is appreciating the proportion. The denominator is also very similar. You'll see the P times Q divided by N, right? And you'll see that back here, adding those in. So the reason why this equation is used is because it's kind of a variation of what we've used before. Since we're using proportions, we're not going to use the z-score that we learned originally, which would be the z equals x by an, oh my, that's so horrible. We fix that. Which is z, which is x minus x bar over s. No, we're going to use one of the modified z's that we've used with other chapters that look more like this. And as we're growing a little bit more in the class, in the statistics course, we know that we can sit back and, well, we don't know, but the statisticians know that they can modify this equation like this so that we can compare two proportions. And that's just a reason why we use such a weird or complex equation.